hope you're doing good. So in this, I'll be explaining the whole slides. So let us begin. Yeah. So let us begin with the industrial context. Carbon steel pipelines forms the backbone of our modern energy infrastructure, transporting high pressure volatile fluids over vast distances. Over years of operation, these pipes are subjected to uh, cyclic mechanical stresses and environmental corrosion. These factors then lead to the stress corrosion cracking. If these cracks propagate unhinderedly, they lead to catastrophic structural ruptures. Uh, there is an urgent industrial demand for high reliability, non destructive surface scanning systems capable for this inline and detection or ILI tools. Okay, uh, it is important to define the geometric nature of these defects. Pipeline cracking primarily manifests in the longitudinal or axial direction, parallel to the center of the pipe's central axis. While a standard inspection method excels in detecting circumferential wall loss, narrow axial cracks present a unique detection challenge due to their microscopic width to depth ratios. So our research is focused specifically on optimizing electromagnetic induction sensor to maximize the sensitivity of these narrow longitudinal boundaries. Okay, so to address this, we look at the physics of eddy currents operating under Faraday's and Lenz's law. Uh, an alternating current in the transmitter coil is generates a time varying primary magnetic field. So this field is placed near a conductive carbon steel pipe. It induces circular loops of electrical current in the carbon steel pipe known as eddy currents. So these currents generate a secondary magnetic field that opposes the primary field due to Lenz's law, modifying the coil net electrical impedance. Okay, when a crack is present, it breaks the conductive path, altering the electrical impedance of the coil, which we measure, and that's how we are detecting the cracks in the pipe. Okay, so next we have a block diagram. So here we outline the closed loop methodology of our inspection system. The signals chain start at ESP32 microcontroller, which generates a high frequency PWM drive signal. These are amplified by a gate driver to switch a complementary MOSFET half bridge, exciting the series resonant LC tank. The resonant current is converted to a voltage by a current sensing resistor, and this signal is amplified by a low noise preamplifier, rectified by an active peak detector, and smoothened in a DC envelope. This envelope digitalizes the ESP32's ADCs, completing the loop to allow real peak time tracking and signal logging. Okay, now the next slide, it explains the electromagnetic skin effect. So an important physical constraint in the electromagnetic testing is the skin effect. Alternating currents do not distribute uniformly. Instead, the current density decays exponentially from the surface inward. From the surface, the skin depth donated as delta represents the depth at which the current density drops to approximately 37% of the surface value. The skin depth is inversely proportional to the square root of operational frequency, electrical conductivity, and magnetic permeability. Because carbon steel is both highly conductive and highly permeable, eddy currents are confined to an extremely thin surface layer. On this slide, we'll examine the skin depth calculation for carbon steel, assuming a conductivity of 5 million Siemens per meter and a relative permeability of 80. At a low frequency of 50 kHz, the skin depth is 112.5 micrometers. At 100 kHz, it drops to 79.6 micrometers. And at 200 kHz, it reaches 56.3 micrometers. So based on these calculations, we selected a nominal operational frequency of 100 kHz. This confines the eddy current to the top 80 micrometers of the pipe surface, ensuring maximum sensitivity to surface breaking cracks. Now let us examine the geometric insertion between the induced current and the defect. Standard ECT probes use circular coils that induces concentric current loops. When scanning for an axial crack, these current loops run parallel to the defect boundary at a key location. Because current can flow along the crack without crossing it, the current path is barely deflected. This results in an extremely small change in the coil impedance, making axial cracks almost invisible to the standard circular sensors. So, to overcome this geometric limitation, we orient our sensor core circumferentially around our pipe relative to the pipeline axis. This forces the magnetic flux lines to bridge the pipe surface in a loop, inducing eddy currents that flow circumferentially around on the circumference of our pipe. Because the currents are focused to flow in this direction, they hit an axial crack perpendicularly. The crack acts as high resistance obstacle, forcing the currents to flow under or around it, which causes a significant change in the coil inductance and resistance. Standard ECT platforms measure raw impedance shift, which are often drowned out by cable noise and temperature drift. To resolve this, we implement sorry to resolve this we implement a resonant mode eddy current testing by replacing the inductive coil in a tuned resonant tank. The inductive and capacitive reactance cancels out at resonance. This concentrates the circuit's energy, making the current highly sensitive to any shift in the coil's parameter. A minor crack induced shift in inductance detunes the tank, resulting in a dramatic change in current amplitude. Okay, we designed the resonant tank in a RLC configuration. In series resonance, the circuit impedance drops to a minimum uh, equal to total series resistance, allowing maximum current to flow. To capture this current, we place a zero point 0.5 ohm non-inductive current sense resistor on the low voltage side of the tank, uh, concentrated to analog ground. This ground referred current to voltage conversion isolates our amplifier from the high voltage switching noise, bypassing a need for complex differential input amplifiers. Now let us review the nominal parameters of the resonant tank on our PCB. The coil inductance is designed for 150 microhenries. The tuning capacitor designed as C105 uh, is 18 nanofarad, and our current sense resistors is 500 milliohms. Based on these parameters, the nominal resonant frequency of the circuit is calculated to be 96.86 kilohertz. The quality or the Q factor represents the ratio of stored energy to dissipate energy per cycle. With a total series resistance of 3.5 ohms, the nominal Q factor calculated to be 26.08, yielding a resonant bandwidth of 3.17 kHz. This Q factor represents a carefully calculated engineering compromise. A higher Q would increase amplitude sensitivity but make the peak so narrow that slight environmental changes would cause complete detuning. So our design provides high sensitivity while maintaining a wide enough bandwidth to track changes. The physical sensor uses a nickel zinc U core. The higher resistivity of nickel zinc ferrite minimizes core losses at our 100 kHz frequency. This winding consists of 100 turns of AWG32 magnetic wire wrapped around the core legs, protected by a layer of Teflon tape. The completed assembly is sealed in an epoxy to prevent the wires from moving under high frequency electromagnetic forces, which would otherwise introduce mechanical noise and drift. The number of turns was mathematically calculated by using the core's inductance factor AL. Tight, neat layers are critical to reduce leakage of flux. For future high volume integration, we recommend using Litz wire because it consists of multiple individuality insulated copper strands woven together. It prevents AC skin effect loss within the coil itself. This keeps the series resistance low and preserves our higher Q factor. Moving to the switching and drive electronics, the gate driver is the TC4427A. This dual gate driver translates the 3.3 volt logic signal from ESP32 into high current 5 volt output. Fast switching is essential to minimize transition power loss in the MOSFET. To support this, three 4.7 microfarad decoupling capacitors are placed directly adjacent to the IC pin to deliver the necessary peak gate charging currents. The inverter stage is built around DMH C3025 LSD MOSFET array. We configure it in half bridge mode by grounding the leg B drains, allowing us to drive the series tank from leg A with a 0 to 5 volt square wave. The gate driver switches the N and P channel gates, resulting in a peak resonant current of approximately 1.28 amps. The analog front end uses the OPA2365A IDR dual operational amplifier. Op-amp A is configured as non-inverting preamplifier with an AC gain of 11. It amplifies the low voltage current sense signal across our resistor R1. I think it's 169. The OPA2365's 50 megahertz gain bandwidth product and low noise floor of 4.5 nanovolts per root hertz ensure high signal at operating frequency. Because the preamplifier operates on a single 3.3 volt supply, it cannot process negative AC voltage. To resolve this, a resistor divider creates a stable 1.65 virtual ground node labeled as V bias. By referring this preamplifier to V bias, the entire current sense AC wave is shifted offset, allowing full wave amplification without clipping. A 10 microfarad capacitor filters out high frequency noise from this reference. Next, the signal is AC coupled to remove the 1.65 offset and pass to the active peak rectifier using op-amp B and the BAT54S Schottky diode array. The op-amp's feedback loop dynamically compensates for the diode's 0.3 volt forward voltage drop. This active peak detector provides linear AC to DC conversion down to millivolts level, feeding a clean DC representation of the current amplitude to the microcontroller. The rectified DC envelope smooth by parallel RC load consisting of a 10 kilo ohms resistor and a 0.1 microfarad capacitor. This creates a 10 millisecond time constant, which is slow enough to filter out 100 kilohertz switching ripple, but fast enough to track rapid amplitude changes during the scan. A 1 kilo ohm resistor and a 100 picofarad capacitor can provide an additional high frequency isolation before routing the signal to ESP32. The digital code is ESP32 S3 ROM1. The NCPWM peripheral generates a 100 kHz complementary switching signal. A critical configuration in the MCPWM Hardware is the insertion of 100 nanoseconds dead time delay. This delay ensures that the high side MOSFET is completely turned off before a low side MOSFET is turned on, preventing the current shoot through. The smoothened envelope voltage is digitalized by ESP32 pin 4 using the internal 12-bit SAR ADC. This provides a resolution of 0.8 millivolts per step. To eliminate high frequency noises from the measurement, the firmware takes 32 consecutive analog samples and computes a rolling average. This results the output voltage is then packed and transmitted over USB serial to our host software, that's MATLAB. Because cable lengths and winding tolerances shifts the nominal inductance, the initial resonant frequency is variable. On startup, the firmware executes a sweep from 50 to 200 kHz in 50 Hz step. At each frequency, ESP32 measures the envelope voltage. The frequency that yields the highest voltage identified as the resonant peak, and the system automatically locks on the maximum sensitivity. To handle lift-off variations and thermal drift during inspection runs, the firmware runs a dynamic peak tracking loop every 1000 milliseconds. It measures the envelope voltage at the current frequency and at plus and minus 1 kHz. If a neighboring frequency yields a higher voltage, the drive frequency shifts to that value, ensuring the system remains locked on the resonance. We developed a real-time MATLAB user interface that connects the ESP32 over serial to 115200 baud rate. This script praises the incoming data stream and displays a dark theme dashboard. It plots two real-time subplots. The top graph displays the envelope voltage to indicate defects, and the bottom graph plots the active track frequency. It also logs the raw data to MATLAB workspace. Now let us examine results. So this figure shows the simulated current sense voltage curves. In the defect-free state, we shown in the dark blue, the resonant peak is at 96.86 kHz with a peak voltage of 454.7 millivolts. While crossing an axial crack shown in the dashed red line, the inductance dropped by 5% and the resistance rises, shifting the peak upward to 99.37 kHz. Operating at our fixed 96.86 kHz drive, this frequency shift detunes the circuit and causes the output to drop from 454.7 millivolts down to 263.7 millivolts. This represents a sharp 42% drop, validating our sensitivity. Okay, the figure represents the simulated real-time data logged of a crack crossing. The top graph shows the envelope voltage in healthy section. The signal remains stable at 2.5 volts but drops to the minimum of 1.7 when crossing crack, showing a sharp 32% dip. The bottom graph shows the tracked frequency. The tracking loop successfully detects the shift incrementing the frequency from 96.86 kilohertz to 99.37 kilohertz. An upward shift of 2.51 kilohertz, the dual indicator reads out, provides clear uh, confirmation of a crack detected. We verified the physical PCB layout using a four-layer stack-up. The analog ground and digital ground planes are separated and connected at a single star point near the power point input. This isolates the high current switching noises from the sensitive preamplifier. High current paths are routed with short 40 mm width copper traces, and decoupling capacitors are placed close to the active IC. Looking at the 2D track routing, the path from the H bridge to the terminal block is kept as short as possible, minimizing stray inductance. We routed a ground shielding ring around the preamplifier's inverting input to guard against leakage currents. The analog and the digital rails are isolated, and the external probe is connected via a shielding coaxial cable to ground the sensor loop. In conclusion, we have designed and validated a resonant mode inspection system optimized for axial crack detection. The series resonant tag and the H-bridge drives successfully translate micro impedance shift into large voltage drops, which are rectified and logged in real time. For future upgrades, I recommend implementing a digitally programmable band pass filter to automatically adjust the bandwidth during frequency tracking, and upgrading to dual channel lock in demodulation for complete impedance plane phase detection. Uh, Thank you, and I think that's all.